Welcome everyone to this GeoDict online seminar. My name is Anton du Plessis and I'm joined today by my colleague Jonas Scharbernack. We are happy to present this seminar on image processing and image analysis using GeoDict. Just as an overview, what to expect in today's seminar. In this live demonstration, you will get a real feel for the software and you will also be able to repeat these steps to import CT dataset, applying non-local means filtering to remove noise, segmenting using global thresholding, in this case with the Otsu threshold, and then porosity quantification using the module called PoroDict, including how to make plots, save images, and save a PDF report, which is automatically generated in the process of running this analysis. Also, it's possible to automate all of this with a macro, and Jonas will show how that works. That's what we want to focus on, and this is what we will show you today in the live demonstration. So today's online seminar title is Extract More Insight from Micro CT Data with GeoDict Image Analysis. We are happy to have you join us today, and my colleague and I will do our best to keep you entertained. This will be roughly 45 minutes to 1 hour. So just as an overview, what to expect in today's seminar. First of all, I would like to introduce GeoDict because there are many participants here who don't yet know about GeoDict at all. There are also many existing users of GeoDict in the audience who want to learn more about the image analysis capabilities. So it's quite a broad and diverse audience, and I think it's worth to present a bit of an introduction to present the context of this work. So I will present the simulation tools that GeoDict is well known for very briefly, and the typical GeoDict workflow, which then explains the context of where image processing and image analysis tools are used already for many years and are for now being, we're putting the spotlight in this seminar to showcase the strength of this capability in particular. I will also introduce the software generally in terms of its modular style, the different kind of modules that you can make use of. And this will be followed by the live demonstration by Jonas. In this live demonstration, you will get a real feel for the software, and you will also be able to repeat these steps if you take the recording of the seminar and take the same data from our website, which will be available. And with a trial license, you can repeat these exact steps to import CT dataset, a small one that we have available for easy demonstration and easy training, applying non-local means filtering to remove noise, segmenting using global thresholding, in this case with the Otsu threshold, and then porosity quantification using the module called PoroDict, showing a number of things, including how to make plots, save images, and save a PDF report, which is automatically generated in the process of running this analysis. Also, it's possible to automate all of this with a macro, and Jonas will show how that works and how to do that for yourself to repeat the same steps on multiple data sets, which is very useful. Finally, after the live demonstration, we'll have some additional information and like how to get started, how to get a trial license for the new users in the audience. And finally, a Q&A session where we'll answer your questions. During the session, you can type your questions in the Q&A box, and we will answer questions there as we go along live. But some of them we will leave until the end, and at the end, you can also type your questions at that point. So let me start with a bit of an introduction. This will be about 10 minutes or so. So for the new users in the audience, what is GeoDict? It is a digital material laboratory, which is a software solution for multi-scale 3D image processing, visualization of 3D data sets, material property characterization from this 3D data sets, modeling of materials based on this, and simulation-based material development and optimization of physical processes. So that's quite a mouthful, and it's all based primarily on simulation strengths of the software. It's an engineering simulation software for microstructural materials engineering. It's well known for this, and examples, I've got one slide for each business area that we focus on. These are some simple examples to get an understanding, not at all comprehensive, just to show some of the capabilities. So the first is mechanical simulation. So you can take a CT scan like of a foam material. This is an aluminium foam which has been CT scanned. On the left-hand side is a compression experiment, a compression test with a number of CT scans at different stages of compression to visualize how the foam is compressed. On the right-hand side is the single before state CT scan, which is then having GeoDict simulation applied to it to simulate large deformation compression. So you don't need to make multiple CT scans to get that result. You can simulate many different kinds of compression and tensile mechanical behaviors. In this case, for the metal foam, it's interesting to get the stress strain curves up to the plateau stress and to get, you can compare the actual results to the simulation and get a very nice plateau stress there. So that's one example of mechanical simulation in what we call the digital materials business area. The other area where our software finds strong application is in digital rock physics or digital core analysis. This involves understanding fluid flow and mechanical properties as well for rocks, for porous rock materials, to understand how single-phase fluids flow through rock pore spaces. Also to understand multi-phase flow, like when you're pushing one liquid through and seeing how another liquid, for example, oil, gets displaced out of pore spaces. This is called digital special core analysis or digital SCAL. And then at the right-hand side, there's a little animation showing mercury intrusion porosimetry with pressure drop, giving you pore size versus pressure, which is a typical lab type of measurement, which can be simulated also based on the 3D images. So this is focused on the oil and gas industry, obviously. The third business area is electrochemistry, which is quite a broad topic. There's a number of different applications in there, in batteries and fuel cells. And in this example here, which is from a validation study, you can see from left to right a single electrode of a battery being charged as the state of charge increases, and seeing how the cell potential changes, where there is experimental data also available for a single electrode. So we simulate ion transport and lithium distribution across the material spaces in the electrode at high resolution. So this allows you to understand battery performance and apply many different simulations at different, for example, different charge rates, and understanding the battery performance and seeing, for example, if there are bottlenecks, if there are in certain areas hotspots which can create problems. We have also a business area called filtration, which makes use of CFD simulations with particle flow. So you simulate fluid flow through porous filter media, simulate how particles are transported through this filter and deposited or captured, and then you can simulate the filter performance based on that. So there's a little animation showing how particles flowing from top to bottom through this material are being captured, and as they are captured, the flow becomes more and more difficult, and the pressure drop is changing over time, with a filter having a cake developed at the top. So these are the kind of application areas where GeoDict finds very strong application. These are business areas called filtration, electrochemistry, digital materials, which are foams and fibrous materials, and digital core analysis, referring to the oil and gas examples. As you can understand, all of these require image processing and image analysis as a fundamental core capability in order to reach those high quality simulations of real materials. And now this topic on its own is also interesting, also without simulation. So we're putting a bit of a spotlight on that at the moment. So the typical GeoDict workflow is like this from left to right. You collect CT data, analyze and segment the material. So there's a digital segmentation and a digital representation of the structure. Like in this case, there's a fibrous material which has all the fibers segmented and separated. And then you can apply simulations, like with this animation showing some fluid flow simulation. This clearly gives you unique material performance information about the permeability or the tortuosity and so on. You can apply, the benefits is, of course, you can apply simulations across the material, across many different angles and with different, by modifying the parameters, like making the fibers thicker and making the numbers of fibers more or less, you can get more information than you can in a physical laboratory, which is useful. But it's also useful to stop just at that point and make use of the already available excellent quantification capabilities. All these materials are already segmented and analyzed to quite high degree of analysis without simulation. So there's quite good quantification that can help you already to understand if your material is too dense or probably too porous or not porous enough, which immediately helps you make good business decisions and helps you to simplify the task. So that's what we want to focus on, the simpler side of GeoDict in a way. And one example is porosity analysis, which is the topic for today's seminar. And here is an example of this. You have a sample with some internal pore spaces. These are then segmented quite easily and analyzed automatically, giving you a nice 3D color-coded image and statistical plots, which you can save to images and to reports. And this is what we will show you today in the live demonstration to reach this result. So GeoDict is a modular software. There are many different modules for different types of simulations. The ones I've shown are only selected ones. There are many more capabilities. The ones that you need for image analysis, typically analyzing images from CT machines, CT equipment without any simulation necessarily, is the import module, PoroDict for porosity analysis, MapDict for material statistics and wall thickness analysis and related topics, FiberFind for fibrous materials to analyze, for example, the angles of fibers, and GrainFind similarly for granular materials. So at this point, I can just say that these, at any point, you can also upgrade and change your setup. It's not a selection which is fixed in stone. So now for the practical side, I've already given an introduction and a background and a context of this. So while we are doing the demo, you can type your questions in the Q&A box and I will answer them as we go along or at the end. So thank you. At that point, I will hand over to Jonas, my colleague, and he will do a live demonstration for you.
Hello and welcome also from my side. My name is Jonas Scharbernack. I'm part of the support team at Math to Market. And in the next few minutes, I will guide you through a typical workflow of importing an image, segmenting it to get a digital model, and then computing some properties on the pore space. So we will start right with GeoDict. I've already opened it. So the first thing that we typically recommend you to do is to prepare a dedicated project folder for your work. This allows you to separate data sets or different projects cleanly and have all the files that you're generating with GeoDict associated only with this specific project. So to do that, I will click on the folder icon here in the top left, click Select Project Folder, and then I'm brought to the default project folder that's created when you install GeoDict, and I've already prepared a specific folder for the online seminar that I will select. Now everything that I will do in the next few minutes will be saved inside of this folder. Now, of course, the first step that we need to do is to get our micro-CT data set into GeoDict. To do so, as Anton already mentioned, we need one of our import modules. You find all the modules in GeoDict here in the top in this menu bar. And of course, we need to go to the import option. And then we select import GeoVol, which is for importing gray value data sets. So for example, micro-CT. We also have a module for importing CAED data. So I will select the import GeoVol module, and then you see that there's a change here in the bottom left of the user interface. and the corresponding module section is shown. In this case, we only have one option here, so we only have the browse option to browse for the dataset. And that's what we do. We click on it, and then we get our file explorer. And now we need to navigate to our dataset. So I've saved the dataset I'm going to use today inside of the default project folder. And as you can see, it's in this folder. It's a concrete material, and we already have the voxel length inside here, which will become important in a few minutes. Now I go into this folder, and you can see this dataset consists of a TIFF image stack. So I have lots of TIFF images that I want to import here. GeoDict can import a large variety of file types. If I expand this list, you can see all of them. If you encounter any file type that you want to import that we don't have available, please contact us. We typically can make that available quite quickly. So for image stacks, of course, we cannot select a single file because we have lots of TIFF files here. It's sufficient if you select one of them, for example, the first one, but can be any one. And then you can click just on Open. And this brings you to the geometry import dialog. This dialog looks slightly different depending on what file type you're importing. So what we are currently seeing is representative of image stacks. At the top, we see the dimensions of our image in X and Y direction. We also have the option to already crop some of parts of the image. This allows you to, if you are certain that there are some parts of your images where no sample material is contained, for example, then you can already crop this part, which allows you to save a bit of memory space and also speed up the import process for very large data sets. But in case you don't know anything about the data set, just import the complete thing. The import all files in folder option is pretty much the same, only for the Z direction. So you can also select only a certain range of images if you want to, but I'm importing everything there. Then we need to provide the voxel length. So the voxel length can be written in the file name sometimes, then GeoDict can recognize it. In this case, it's not. It was only written in the folder name. So we need to put it in manually, and it was 72 micrometers. If you need a different unit, you can change them here in the top right of the dialog, for example, to nanometers. And that's all that we need to do, and we then can click on image processing to proceed with the next step. The image processing is done in a completely separate dialog that just opened. Here you can see your data set in all three spatial directions. And in the bottom right, you see, for example, the histogram, but there's also a few other options that I will show you in the next few minutes. Here at the top, you again have some menu options, for example, for saving files. And below you have some options for the visualization. So for example, you can adjust the gray values that are shown to change the contrast, as you can see when I move the slider here. Or you can control what overlay is shown. So overlay is typically showing you what kind of cropping, rotation, or so on you're doing to the dataset. We will also see a few of those options today. Then you have options to change the view mode. So currently we're seeing everything together. We can also change that to basically only have one of those options active at a time, which allows us to zoom in a little bit further. I will switch back to the tile view for now. Zooming is either done via these buttons here, where you have predefined zoom levels that you can just select by clicking on these buttons, or you can hold your right mouse button over the image and move the mouse up and down, and then you can just zoom into any level that you would like. So as I said, in these individual slices, we are currently seeing one of those slices. We can of course change that by either moving this slider here or hovering over the image and using our mouse wheel. And we can also see where we are currently located in our dataset by looking at the other two slices where we have this red line indicating the currently selected X slice. So in the histogram at the bottom right, we see all the gray values in our dataset and the distribution. The 3D preview gives us an overview of the currently selected slices. So somewhat of a first impression of what our dataset looks like in 3D. If I move the slice, I also move the image in the 3D preview here in the bottom right. And then we have the mean gray values per layer in each of these directions. This can help you to identify some artifacts that might be, depending on the measurement, might be available in your data set. So the first thing that you typically do when you have the data set loaded is to get rid of any empty space around the data set, because it does not contain any information for you. And it's also then, of course, increasing the memory requirements and also slowing down any further processing. So to change the image size, we go to the image processing here on the left and then click on image size. And here are all the options that influence the size of our image. And what we want to do is crop away some of this void space around our sample. So when we expand this, and now if you click inside of this, you activate the crop overlay automatically, which you see here at the top. Currently, it's not very clearly visible, but when I move one of those sliders, you see that we now have a yellow box inside of our images that indicates the area that I will keep after I crop. So everything outside of this yellow box will be discarded after I do the cropping. I can change the dimensions by using, again, sliders, entering manual values, or I can also hover over this yellow box here in the images directly and adjust the range. What is also very helpful if you are just cropping empty space around your sample is using the suggest button. So the suggest button basically uses a simple threshold to determine where you actually have sample material, so some solids, and just keeps all of that solid material, and everything else, so every basically layer slice that does not contain any sample material will be discarded. So if you click suggest, you see that the yellow box is quite nicely adjusted here on these three sides. The fourth sides, there seem to be some changes or some differences in the gray values, so it's not very nicely capturing the sample. For this, we can change the threshold value. For example, we can increase it a little bit, and then click suggest again, and now it works quite nicely. And once you have set that up, you just click apply, and then the sample size is changed. So we have decreased our size in total, and we only keep the sample material itself. The next step that you typically perform is some denoising. So it's quite common, and we can also see it in this data set here that you have noise, so like this graininess in the image after the measurement. And there are some options that you have to get rid of that. The recommended one that we have available is under image filters, here on the left side again, and then the non-local means filter. So the non-local means filter basically takes smaller regions around the voxel and compares it to other smaller regions inside of a given search window. So these are these two parameters. The patch radius is the size of regions that I'm comparing, and the window radius is how far am I looking for other patches to compare it to. And the filter strength then determines how much smoothing I'm applying to the data set. So even though I might know what these parameters are, I'm not exactly knowing what the correct values here are for the data set that I have. And to help you with that, we have this preview option. When you click it, you get this new dialog where you only apply the filter to a small section, 2D section of your data set. So it's quite fast. And it allows you to test different values for these parameters. So just to highlight it, we can just select this. I will increase the zoom factor a little bit. I will keep the X slice that we currently have. I want to apply it on a range of roughly 100 by 100 and somewhere to the center of my image. And now down here, I can select one of these parameters that I want to vary. And then I can select different values. So for example, let's look at the patch radius. The default value is 1. But let's see what happens if I use a patch radius of 2 or 3. So when I click this create, it's very quickly applying the filter to only the small section of my data set. On the left side, I see the original image. And then I see what happens if I increase the patch radius. So the default value of 1, 2, and 3. And here it's clearly noticeable that I start get a very blurry image if I increase it too much. So a patch radius of 1 is quite sufficient. I get rid of all the noise, but I still have clear boundaries. So for the patch radius, I can keep a value of 1. For the window radius, the default value is 3, so let's just vary it around this. And here I can see that there is also a little bit of a blurriness effect, but lower value also does not get completely rid of the noise. So either a value of 3 or 4 is probably nice. And then the last thing that we want to vary is strength. So for the strength, I can also define the step size in which I want to vary it. And let's just vary it from 0.1 to 0.5 in steps of 0.1. Once I click create, I can clearly see that 0.1 is insufficient. I still keep the noise. And at 0.2, I get rid of the noise. And then as I increase the value further, I start to get blurriness again. So 0.2 is completely sufficient here. Now, once you have a complete set of parameters that you like, you can click on this option. Then it gets this red box around it. And now if you close the dialog, they are automatically transferred to the parameters here. And then you just need to click apply, and it's applied to the complete data set. So it only takes a few seconds for this data set. That, of course, depends on the size. And now we got rid of the noise, and it's much easier to distinguish between these grains that we have in our concrete and the matrix materials in between. So now that we have a nice data set and completely finished processing, in this case, we can continue to the segmentation. So segmentation meaning I'm creating a digital model that I can use in GeoDict out of the data set. Before we do that, typically we recommend that you save the process data set in case that you want to go back to any of the image processing. Maybe you want to apply some other filter afterwards, and then you don't need to repeat all the processing steps that you have done until this point. To save the data set, you can go to File in the top left here and click Save as 3D Image. Then you need to provide a result file name, which is both the file name of the dataset that you're saving and also the corresponding result file that we will see in a second. As the sample was called concrete, I would also call this concrete. And we have processed our dataset, so I would call it concrete processed. Then you can choose between different data formats. That depends on what you want to do further with the image. If you want to continue working with GeoDict in the future, we recommend our own data format because it contains all the relevant information that you need, and it's also more efficient to load. And then I just click Run. And once it's finished, it opens the result file, which I just mentioned before. And these result files are a typical product of any computation or any process that you run with GeoDict. And the content depends on what you are doing. So in this case, it doesn't contain too much information. It only contains some information of the data set that you saved. And the interesting part, it also contains basically the operations that you performed on the data set. So in this case, the cropping, which is called change image size, and the non-local means filter. So if you keep this file, you know what you did to the data set before saving, which is nice if you want to repeat these steps at some point. So I will close the result file because I don't need it any further. And now we can proceed to the segmentation. Segmentation is also here on the left side, but in a different tab. The image segmentation, you have different options available here. The default and simple option is the global thresholding. So basically determine single threshold values where you differentiate between different material phases in your sample. For more complex samples, we also have AI segmentation where you train and apply your own AI models. We have models with varying complexity that you can then apply to the data sets if thresholding is not sufficient. For this data set, the materials are quite clearly distinguishable, so we can go to the thresholding. And these options here on the left are the ones that we need to define further now. So when I click into the section, I again get a new overlay, the segmentation overlay. And this shows me what material phases are separated when I do this segmentation. So currently I have two materials. I have my solid, which is red, and pore space in white. And the threshold is automatically determined by an algorithm called OTSU, which is here under this method. So the first thing that I'm doing now is also give it a new result file name. because the default one is just from the image that I clicked on. And I will call it concrete again, and I will call it Otsu, because that's the algorithm that we are going to use. Under the segmentation mode, you define whether you want to do a single threshold, which means you only have 2 materials after you do it, or if you want to do multiple thresholds, so you have more than 2 material phases. So just to show you, if I select this option, the threshold method automatically switches to manual, then I can manually change these values. But there's also the option to use one of these algorithms. So for example, the Otsu. And when I do this, you can see that it's also quite nicely able to segment between the pore space, the matrix material in red now, and the grains. So in case you want to analyze grain shapes inside of your sample, this might be the option that you should go for. In our case, we only want to focus on the pore space today, so it's not really necessary to separate between different solid phases. So I will switch it back to single threshold. Now we have the Otsu segmentation method determining our threshold value. That's why you don't see it. You see it only in a grayed out value and you cannot change it. Then there are a few optional things that you can do at this point. You can change the materials. So currently we have a default pore space and a default solid. You can use our material database, for example, to fill it with air if you want to do it, which then automatically is transferred later on if you run some of the simulations, for example, simulated flow, which is dependent on what fluid is inside our sample. We don't really need to do it at this point, so we can just leave it as the default values and click Create Segmentation. Now, again, we get one of those result files. This result file is very similar to the one that you get when you save it. You only get some more information about the thresholding up here and about the digital model, or what we call in GeoDict the structure here, so the percentages of pore space and the solid. I will close it. And I will also now close the image processing dialog because we are now finished with this step and go back to the main user interface. Now here you also see a 2D visualization, and at the moment we are seeing 2 things at the same time. We are seeing the gray value dataset here as well as what we are calling a volume field. This is the black color that we are seeing because there's void. And then in red here we see our digital model, which is the segmented structure that we got out as a result. So I don't really want to see the gray values anymore. I will turn off the volume field. And then you only see the segmentation results. And similarly to what you can do with the slices, you can also in the 2D view here slice through the structure. So through a digital model that you generated. We can also switch up here to the 3D view. We get some nicer camera options to, for example, show outlines, halos, shadows, give you more of a 3D view of this data set. And another option, because currently we are seeing all the single voxels that are the basis of the GeoDict model, we can also change to a smooth rendering of the surface, which gives you a bit more of a nicer visualization option here. Now, you can, of course, inspect the data set in 3D after you finish the segmentation, but this is also the basis for everything else that you can do with GeoDict. For example, what we are going to do now, the pore analysis. The first thing that we want to do for this type of pore analysis is we want to focus on the internal pores of the sample, so not the pore space that we currently have around it. And of course, for this, we need to separate them. And to separate them, we go to our pore analysis module, it's under Analyze up here, and then PoroDict, which is for analyzing the pore space. Get this new module interface here in the bottom left. And to separate the pore space, we are using the open and closed porosity functionality. This allows you to separate pore space into open pores, which means they are connected to one of the boundaries around our sample, so to one of the sides of this box that we see around, and closed porosity that is not in any way connected. So if you click on Edit, you get some more additional options that you can define before running it. So you can specify a result file name. I'm happy with the one that I have. You have some parallelization options depending on the license and the computational hardware that you're using. Then you define these inflow planes, which means which of the sides the pores should be connected to be considered open. In this case, I want everything that's connected to any of the sides to be considered as open pore space. And then the important option that we need here is write open and closed pores as a GDT, which is the GeoDict structure, so the digital model. So we get a new structure out of it. Then I can click OK and just run. Just takes a second. And I get the new result file. This gives me some idea of the porosity percentages in my new structure. But the important part that we need here is under data visualization, I can load my pores as a structure. So I can load a new digital model of my sample. So when I load this and close the result file, I firstly see no difference at all. When I look at the legend here in the top left, I see that there's now 2 material IDs for the pore space. So this ID 2 is new, and this only contains the closed pores. I'm not seeing them right now because they're of course inside of my sample. So to see them, I can go to the right side here, the color and visibility options, and make my solid invisible. Now my solid is invisible and I only see the closed pores that are inside of my sample, and I can inspect them visually at this point. Now in the next step, we want to analyze some of the properties of these pores. And the best way to do this is again go to PoroDict and choose the Identify Pores option. The Identify Pores option basically identifies every single pore in the dataset that you have and gives you loads of properties for each of these pores. Again, when we click the Edit button, we get some options that we can choose from. The first thing that we need to define is what do we want to apply the computation on. We want to use our current structure. We can define a minimum pore diameter. And then we need to change, what we need to change here is what we want to analyze. By default, we're analyzing the complete pore space, but we don't want to consider any of the open pores here. So I will choose here the option to only apply this computation on chosen material IDs. And I only want to apply it on my closed pores, which is the ID 2. Below, we have some option where you can control how pores are separated when you have a pore network that is connected. So with pore bodies and pore throats, there's a measurement of once if you want to reconnect pores that have a certain area that they are touching with. In this case, I only really have these isolated pores inside of my sample, so I want to switch that to 0. And then everything that is touching would be reconnected afterwards. Everything else we can leave as default. And additionally, we have a few of these output options that provide you with a large number of file types that you can generate using this computation. I'm not really interested in any of them. The only thing that we want to have here is to see our pore size also visually in the 3D view later on. So I will activate this option. And then I will click OK and run this option as well. So this only takes a few seconds again and gives me a new result file. And now this is one of the more extensive result files that we have available in GeoDict. Firstly, we get a report. This report gives us some information, for example, the number of pores that it counted. So in this case, 219 individual pores were identified. It gives me some statistics on the pore volumes in relation to percentage, or in basically the absolute volume, some indication of the sphericity of the pores, some indication on the diameters, the coordination number, meaning if the pores would be touching, how many other pores are they touching? In this case, it's of course 0 because I merged everything that would be touching. And then some orientations of the pores. All this data is also used to create a large number of plots here, which you find under this tab. And for example, if we switch to the diameters here, you see the distribution of diameters in relation to the volume of each of these diameters. So we see that we have one large pore with a large diameter, and this is of course producing a large bar because we have a large volume. You can also change these plots by using these options here on the left. So for example, I can change that I don't want to get the diameter in relation to the plot, but in relation to the number of pores that have this diameter. When I click apply, the plot here changes, and you can see that now you have most of the pores have a really small diameter and only a few with large diameters. Another way to visualize this is to look at it directly in 3D. And you do this via this pore visualization tab here. You can load the pores as an index image, which gives you an indication of what are the individual pores that were counted. So when you now go back to the main user interface, you see that all these pores are now shown in individual colors. And each of them has their single ID. So for example, this large pore here has the index image ID 101. And this one is pore number 61, for example. So all of these pores were separately identified and are one of these 219 that were identified total. And all of them have individually assigned properties like the sphericity, diameter, and so on. And all of this data you can also get out of the result file. So when I go back to the result file, we can also load the pore sizes. So in this case, the equivalent diameter of the pore that was computed. And when I now go back to the main interface, you see that currently everything is blue because all the materials that we did not analyze have by default have a value of 0. So first of all, we need to get rid of them. You can do this by going to the volume field and then change the visibility here. So I don't want to have it visible on the pore space or the solid. I only want to have it on the closed pores. Now when I deactivate this, you can see that now they are colored by their ID. So of course, this large pore is the red one, which the largest diameter. Then I have a few larger pores and a lot of these smaller pores, as I saw in my plot before. Now using this report that we have here, the result file, we can also create, we have some export options to get the data into different formats. One option is to, if you click on export down here, is to get it into an Excel file. Then you get all the values associated also with Excel, and you can continuously work with them if you want to. The other option, if you just want to provide an overview of these results to, for example, colleagues that are not working with GeoDict, you can save them as a PDF file. When you click this option, you're automatically brought to your project directory, and it will save it as a PDF file with the same name as the result file by default. So when I save it, it creates this PDF file, and it also automatically opens it in the PDF viewer that you are using by default. It should only take a few seconds. Bring it on screen for you. So now you have this PDF file. It contains all these tables that you saw in the report before, as well as the plots that you saw. And it also contains, of course, the modified version of the plot. So in this case, relative to the number of pores, as you see the diameter as well. So this is something that you can then easily provide to colleagues, for example, after the analysis. Other options to get your results out of the result file is, for example, if you want to get the plots, you can right-click the plot area, copy it directly to a clipboard, and you get the current visualization and can, for example, put it in a PowerPoint presentation. Or you can also save it as an image with a defined resolution if you want to. You can also visualize the 3D viewer here, for example, the diameter showing for each of these pores. You can save images of this in the main user interface if you go to this button up here, save image as, and then again you can save the current view that you have, or you can define a given resolution or use one of our presets. Another nice option to visualize it is you can create videos of this. So videos is the button next to image creation here. And we have a few templates for you to use for video creation. So for example, when you want to visualize a structure, you can use this clipping. Or in the case, if you want to visualize this equivalent diameter from different sides, you can use one of these rotation options, and you rotate the sample and then you view all of these pores and their equivalent diameter from different sides. This takes a few minutes. That's why I'm not showing it to you right now. But if you want to try it later on, you can easily do so. The last thing that I want to mention is the automation option that Anton really already mentioned during his introduction. So all of this is quite easily automatable if you want to repeat, for example, this Pore analysis that we did today on a large number of samples. So you don't need to do it manually every time for each data set, but you can automate it. And this works in GeoDict via Python scripting. So you can create Python scripts, and the easiest way to get started to create it is, for example, by going to the session macro here in the bottom right. When you expand this option, you see that everything that I've done today is also recorded as a Python command, so GeoDict specific Python command. And I can use this as a basis of creating a script for automation. So for example, I could choose the open and close porosity that we did and the identify pores, select them, bring them to my custom macro and save it. This is also then created saved to my project directory automatically, and I can give it a name. And this will be saved then in the project directory as a Python script, and you can open it with the text editor of your choice. To bring up on the screen. And here you can see the general structure of one of those Python scripts. And if you scroll down, you can see the parameters of for example, the open and closed porosity and running it. And now you can, of course, modify this. You can add variables to that. You can do everything that you can do with Python to create your own custom script. And then you can, in the end, execute it quite simply in GeoDict via this macro menu here at the top, and then execute macro script. And then, for example, for my script, this is called now the macro script. If I select it, I can just run it. So I could load a different data set, a different structure now, and also run the same computations. And with this, I will want to conclude the live part of this session today, and I want to hand back to Anton.
Perfect. Thank you very much, Jonas, for that great demonstration. I hope everyone enjoyed that. So, some additional information. The recording will be available. All of you will get a link, everyone that registered for this seminar. The data used here will also be available on our website. It is actually already on the website. If you want to search around for it, you will find it under our section where we have some micro CT data sets. A trial license can be obtained by following the steps, filling in a short form on our website. You can find this form on a link on the front page of the Math to Market website. So as I said, the software is modular and there's different options. So I wanted to say something about that. You only buy the modules that you are interested in, and you don't need to purchase all modules. And you can upgrade it later at any time if you later find out you are interested in adding, for example, flow simulation to your license. This is not a problem at all. We have different license options. You can go for a node locked or a typical floating license, which can be used on different computers with one floating concurrent user at a time or more. Cloud license options are also available for your own cloud usage, or we also offer cloud options of our own. We have commercial pricing, which is the default. We have some discounts for non-profit organizations and even stronger discounts for academic users. So just to be aware of that, the normal way is to purchase perpetual license, which works forever, but it's also possible to have a lease license, for example, a 1-year license, which can be extended after that. For example, if you have a project which you only need the software for some time. We have on our website a very nice learning center with tutorials and training materials where you can teach yourself. And there's even, if you log in with the same email and password that you use when you get a trial license, you get access to even more material on this learning center. We have also formal training options where you can purchase training remotely or on our site in Kaiserslautern in Germany. And for academics, there's a very nice entry point called the Academic Innovator License, which is a light version of GeoDict, which includes quite a large number of simulation tools into the software with only some restrictions on the maximum size of structure. So subscribe to our newsletter. We have a monthly newsletter for upcoming seminars. We continue with this. We like to share what is possible with GeoDict, and we would love it if you share this knowledge with your colleagues and with people that you think might find benefit from our software. So if you have interest to discuss with sales, please get in touch with sales@math2market.de or myself, my name, anton.duplessis@math2market.com. So just a few things to mention before we go to questions. There's a series of blog articles that we have started, which I call the hidden gems, which are little powerful capabilities of GeoDict, which are hidden so far, which are not so well known. The two first ones cover the topics that we did in this seminar, actually. The first about making inspection images and professional reports in GeoDict. As Jonas showed you, you can easily get a very nice PDF report from PoroDict. The same thing is with all the other modules in the software, and there's a little bit more detail in that blog article. The second one is about reusing workflows with macros and recording the steps. So what Jonas mentioned at the end, typically it's an increasing important topic in especially commercial applications to automate work. So we have an annual user conference, which we call the GeoDict Innovation Conference, this year at the end of September in Frankfurt, near the Frankfurt airport. So quite easy to join this conference. Also possible to join online. It's a great place to see specific presentations of applications in more detail, to see customer presentations, what our customers are using GeoDict for, and to network and see the latest features are coming in the next versions of GeoDict. So with that, we can go to the Q&A session, and you can see in the meanwhile some of our happy customers who allow us to share their logos with you. So I will stop sharing at that point and see if there's any other questions. I did try to answer questions as we go along. If you have any questions right now, please type them and we can read them out loud and address them in addition. Let's take this one, which I already addressed, about beam hardening correction options and representative volume element calculations. Beam hardening correction is not directly possible because this is typically handled in CT reconstruction software, which comes with a CT equipment, but it is something that we might be developing. So it's something that you can keep your eye out for. But in terms of REV, we do have capabilities in different modules in the software. So it's not a very easy answer here. I don't know if you have anything extra to add on that, Jonas. Calculating representative elementary volume.
No, not directly. So it's of course possible, but you need to see it for the specific application that you want to do it for. It's of course possible to get subsections of the sample and apply it there and see at what point it becomes not representative anymore.
Okay, there's a new question here. Is there a quantitative measure of the total ellipsoid fitting error in the identify pores calculation?
So you can certainly, you can guess one of the results is that you also can visually get difference image of the two, basically of the ellipsoid that's fitted to the actual pore volume, to the actual pore geometry. So based on that, you can certainly get some also quantitative values out of it. I'm not sure, I don't think it's automatically calculated, but as the results are there, you can of course then compute it based on that. So you for sure get a visual representation, and based on that, you can also compute the error yourself, I guess.
So it's an interesting question, and it's technically possible, but it's not a standard output at the moment. So
yes,
if you have trouble to do that, get in touch with support. I didn't mention that our support desk has a team of expert GeoDict experts that help you with these kind of topics on a daily basis. All right, we have another question. Thanks for the presentation. Because I use the Dragonfly software for the CT data, I wonder what is the major differences. So it's a good question. It's not our aim to compare with other softwares here. All softwares have benefits and strong points and differences. So our strong points are the professional reporting and professional interface capabilities, where I would say that we have very well-polished tools, which are very well established and validated, and adding a lot of value, especially with simulation tools. So it's maybe a topic for a further discussion, but not in this forum. So thanks for that question. Oh, there was one about how to differentiate two fibers of the same type, for example, carbon fiber structure, to apply a contact resistance between fibers. So I did answer there already, explaining that we have, with a fiber find module, very nice algorithms which separate digitally touching fibers. I'm not aware of contact resistance as a property that we employ in our simulations. Maybe you can comment on that, Jonas.
I'm not an expert really in the mechanical simulations, but I think there is something for contact resistance that you can do. It's called the elastic module.
I think it is there, but I don't have direct experience as well on this.
Yeah.
So, but you need to separate them first as a first step,
yes.
And for that, the fiber find module is used. We have normal image processing separation methods, and also an AI method with a pre-trained AI model, which helps with that separation. And then you apply after that the contact resistance. So good question. Thanks for that.
I think in that sense, the fiber find module is quite similar to what we do with the identify pores. So in the end, you also get individual fibers, and all of them have individual properties and so on. So it's quite similar to what we've seen today, just not on pores, but on fibers. And there's also, I think, there was a seminar last year. So if you look up on our YouTube channel, you will find also a seminar on this topic. So you can have a look there on fiber find. Right. So I think that brings us exactly onto the hour. Thank you, everyone, for joining us. And I hope you found that useful and entertaining. And we're always happy to hear feedback as well. So let us know what you want to see in these seminars. We have a series coming up, so please keep your eye open for the next ones. Thanks a lot for joining today, and have a great day further. Thank you.